Hey there, what's up, and welcome to Team Drone. This is the drone in its debug configuration. This is how we flash code onto the drone so it can be local. We have the launchpad debugging system. We have ourselves an SWD bus debugger, if you will, coming from here all the way into the drone. You can see this is the drone fully assembled. Normally, this strap will be here to make it more centered, but this is what we do for debugging purposes. You can see clearances are reserved, which is nice. The drone itself has a thrust to weight ratio of about 1.9 to 1. You want a 2 to 1 ratio. It's a smidge heavy because we have to use a 2S battery, but it's still able to take off given the weight that it's at. And yeah, our bus connects to the computer down here. We have some protection tape here. This is where the power comes and attaches to the battery. As you can see, it's fed through this wire. So we were able to fit the power wires through the spacing between the flight computer and the ESC to deal with the battery, and we're able to fit the JST pin bus behind and under the top of the frame connected to the ESC, all to make a very nice compact module that's fully functional. This drone is able to operate without the need for this board, which we'll demonstrate. The drone can do IMU. It can also do D-shot, which is very nice. It's a way of stabilization for this drone in a basic motor control. However, in order to see the IMU values, we'll typically have the drone connected to the debugger. We track the values on our watch. Otherwise, you can see the motors twitch and you can hear the D-shot activate, which is awesome, to prove that the system does in fact work on the drone. There's a little peek under the hood of the flight stack. You can see that we have our custom PCB computer to the side here. We have ourselves a bridge cable to the launch pad as our debugging system. However, all the programs are local on the MSP M0, as you can see on our flight computer. This flight computer is connected by an 8-pin JST to the ESC, as you can see here. This is a minimum of a 6-volt input, so we use a 2S battery to satisfy that requirement. We have these mini brushless motors that are attached to these tripads. You can see for each motor, these pads deal with the power, ground, and signal of these motors. There is a small little computer that mixes between these motors for us from the code that we make and the firmware we make for the flight computer here. That is communicated through this JST wire. Over here, you can see covered up at the moment is our radio module. Our radio module features one channel. This one channel controls the throttle. The reason being that it's one channel is because during the manufacturing process of this board, what we begin to find is that just melting mere solder on the pads causes them to rip off since they were not made well by JLC PCB. So what we did is we managed to salvage what we could. You can see that this purple power wire is attached directly to the pull-up resistor. The radio is I2C, and we need 47K pull-up resistors. We were able to fix that missing pad, plus salvage the 3 pads there for, the ground, the SCL, and the SDA, as well as one channel pad over here. You can see within this yellow wire. They've been held in place with super glue post solder to ensure that there's some strength to those joints so they don't rip off even more. And then inside is a nano RX, and the RX communicates to the controller. But yes, this is this stack. Here is the drone fully assembled with its stack in all its glory. You can see we had to customize a 3D print mount complete with heat inserts in order to secure all the boards together in the stack. You can see that even with that custom part, we still fit underneath the hood of the frame, which is amazing. You can see the 8-pin JST being tucked snugly in there, wrapped around the flight computer to the ESC. You can see how all the motors are able to spin freely despite the wiring. You can see the proper mounting of the radio unit right here. These wires out here were miscellaneous from channel 2 and 3 that no longer worked, unfortunately. They are removable in this scenario. I'm going to do a custom mounting on the frame in order to deal with the 40mm by 40mm mounting size. However, it all worked out quite nicely. The battery itself is able to slot right on top of the hood. The strap would tighten, the battery would come out, and you would have yourself a fully operational unit. All right, this is what we're using as our transmitter. This is the Crossfire transmitter. This is the Crossfire Nano RX. Here we have the binding system, just to prove concept of the binding firmware that exists here. We're going to click the boot button within here. There, we press the boot button, refresh this guy, and it is in the process of binding. The thing is, right now, we have successfully installed firmware onto this guy, thanks to this. So right now, it's in the binding process. The issue at hand, what we're discovering is this particular radio controller is a little picky. It likes to make sure that all the channels are nominal. However, we're only working with one channel here. So another way to prove the binding of this guy is to go to page. Oopsies, let's go down, sorry. To the agent. There we go, the agent has found devices, TX. You can see all these things. We're going to hit the bind, it's ready. We're going to hit this, it's in progress and loading. And right now it's trying to find this guy. We may have ran into a problem with our power wire going to this. It used to light up red, now it is not. According to the soldering joints, everything seems to be fine, but again, the pads on our flight computer are very unpredictable. So it was the unfortunate downfall of the radio, but we have proven the hardware here that we have went through the steps of manufacturing. We've went through the steps here on the binding as much as possible. So this is our radio module, if you will. Right, this is a design class after all, so let's start from the beginning. This is the Simon board. This is our testing bench to prove that motor control handling the stabilization control was possible. On the Simon board there are 4 LEDs. What we're able to do with these 4 LEDs is prove that with the accelerometer we were able to manipulate the brightness depending on the orientation of the board to mimic real motor control. If a board dips to a corner, that LED in that corner will brighten, as the one lifting up will dim. And it was able to handle this, so I moved on to the actual board itself. This is what we came up with on the physical side. The board you see here was manufactured by JLC PCB. You can see that we have ourselves the pads for the MSPM0. We have an LDO in the top left. We have a horizontal JST connector. We have a small place for an IMU. We had some style points by adding some silkscreen design. We have a bunch of resistors, capacitors of the like, and some through-hole components with switches and the necessary pins for the SWD bus. You can see on the back side we have our own buzzer that we use. You can see here are the radio pads that we had that unfortunately were too weak to melt solder on and were curled up immediately and flaked off, which was very unfortunate. But you can see we have our clock down here, our own clock, 16 gigahertz, and the through-hole components. We have particular spaced mounting holes, and the board looks like this way because this board was designed exactly to spec to aftermarket flight computers. This right here would be considered a 40mm by 40mm flight computer. Here is a fully assembled board. What you see here is our backup board. You can see all of the components here hand put onto the board itself. You can tell from the scorched marks from the solder that was handmade and some minor imperfections in our mounting. You can see that there were some capacitors that were a bit too small, and so I had to take the liberty of doing a solder bridge across that on purpose, which worked fine. It passed the continuity test. Each one of these components you see here were meticulously tested for continuity, which is great. You can see here that we have the MSP M0 in the center, connected to all the various components. You can see we have our LDO at the top left. It regulates our battery, which in this case from this board, VDD is 5 volts, but we want 3.3. So this regulator regulates down to 3.3 for most of the components here. The switch and others will take 5 volts, and so we will bridge it directly from the JST connector itself. You can see that we feature a reset and boot button. This became very helpful to debug our drone, to troubleshoot why the motors weren't spinning when we were going through it. You can see the IMU attached in the top right corner. On the back, you can see the speaker mounted as well as our through-hole components and the clock. You can also see this board being attempted at our solder venture, but you can see the pads peeling off already. This board is here as backup in case we need to use this board. This board lost a channel, but it still in theory can pull off the rest if you are careful and use super glue, which unfortunately we didn't think we had to use because it was the first time for us to realize that these boards and these test points peeled so easily. The switch functions well. It prevents the board from getting fried in case of any event from the ESC overloading it. And yeah, this is the battery. This is a custom connection that we had to design ourselves with an XTC60. This is so that we can have a more secure and better connection on our drone compared to what was already on here. You can see that it is a 2S battery, that it's taped down, and also heat shrink for protection for use, as well as the charging cord here that we can pin down when the drone flies. Just to walk you guys through the PCB just a little more, here's the PCB we have in front of us right here, and here are the design choices that I made. So what I wanted to do was, because this is 40 millimeter by 40 millimeters, in order to model it based off of the ESC, we have the holes to the same spec as the ESC, the same positioning, the same fillet, everything's the same. And from there, I built off everything. I wanted the through holes to be in a position where I can easily access them. So the switch is here and the SWD is here. I also know that this is a flight computer. It's going to need a reset button, a boot button, and they did in fact come handy. I wanted the MCU to be centralized to everything, so I put it as close to the middle as I can. And I orient it logically where the bus coming in from the JST, the 8-pin with all the motor signals, can easily be accessed to as many pins as possible pointing up, and then with a few exceptions on the sides. And same goes to any other components that are associated with the MCU, which you can see down here on the bottom and to the left. You can see that I wanted to take advantage of planes, and so I made all my components have similar nets, so I could do a plane. So you can see the inner ST has their own plane, the ground has their own plane. There's, typical ground planes, but what I ended up doing was, because of how jam-packed this PCB was, I made my own ground planes here, 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 and another one here on the back side, and then I connected them with vias and traces, and that's how I went about my ground plane, because this is way too complex with all the different traces happening here, with all the different moving parts and all the different components here. So with that, you have the JST, you have these on the back. These are test points to mount the wires in order to communicate to the radio. We have our pull-up resistors here for the radio. We have all the necessary typical application components, capacitors, and resistors for everything. Here is our LDO. This is to regulate the 5 volts coming in from the ESC. So everything that needs 3.3 can take it. On the other side, same deal with all of the different components for the buttons that are needed for typical application and what have you. I tied again to take advantage of the planes. Here, as you can see, being really wary of the holes and such. You can see all the vias I had to use in order to get the motors to go where they need to be, or I guess the traces, mind you. The holes have been moved specifically so that we can have some bonus flare with our silk screen. You can see our drone here and the rice owl in the back. But yeah, that's how the board is designed. MCU is centralized. All the components are grouped based off of having similar characteristics, so I can use planes. And then from there, I was basing our through holes off of accessibility. And same goes for the backside. On the backside, you can see all of the things with the clock and the speaker and the RF traces and everything like that. You can see that we wanted to have some advanced traces going on with our RF system here to prevent to have like as little noise as possible. So we try to keep those as straight as we can and directly to the MCU. Same thing goes for the motor signals as well. We're trying to allow there to be less noise, so when we run our stuff, we don't have any heartache later. We've also implemented some nifty little via overlaps in order to reach the necessary pins on the MCU, which was really necessary, which was awesome. And everything is up to spec in tolerances and whatnot, so everything was able to be manufactured, soldered, and the whole like quite well. But yeah, this was built in mind to make sure that there are less noises, everything of the like. We try to keep our 5 volt as localized as possible to this only other thing that takes the 5 volt. And then anything else that has voltage we try to keep separate from all the other components to eliminate noise. Same thing goes for the IMU here. But yeah, in order to help with the noise, we also preferred planes for our voltages here in the back to help with that. But yeah, that's the PCB. All right, moment of truth. The drone is now disconnected from the launch pad. It's free moving. We're now going to prove our firmware. I will be setting my phone down like so. Here's the drone. Be very, very attentive to the sound from the drone. The firmware that we are running for our motor control and our IMU control is called D-Shot. It uses DMA code, which is something we have not done in class. And to prove that the code is working to the viewer, the motors should be moving, in this case twitching. Unfortunately, the motors are not receiving enough voltage as proven with this voltmeter that we use to check. So you won't be able to see any fast movement for this proof of concept, this low viable prototype, but you will be seeing twitching, which is not from the vibrations of the buzzer, it is actually from the motors moving. So if the motors twitch, that proves that our program works. If you hear the sound, that proves that our firmware is actually being taken and executed. So without further ado, I'm going to hush up now and connect the drone. Watch and see. So you might have seen a small bit of movement with the pink propeller. I'm going to disconnect this and flip the drone around in case it's more obvious on the other side. Here we go again. We'll be connecting again to show proof of concept once more. You can see the gyros for our position and the acceleration right now. You can see the acceleration up and down is constant at around 2000 for the z-axis. You'll see change as I grab the drone right now. I'm going to lift it up, boink. You can see some changes here. I'm going to bank the drone to the left. You can see the increases there with the certain ones on the associate axis. I'm going to center it back. You can see it come back down to like the low values. I'm going to bank to the left. You can see the big change in values there and the acceleration as well. I'm going to pitch back 45 degrees. You can see the behavior there. I'm going to recenter, let it calm down, and then I'm going to pitch forward 45 degrees. You can see the increase there. I'm going to pitch it back just a little bit and keep it steady. I'm going to spin it. So there's what happens when I spin it. Spin it again, spin it left, spin it right. Yeah, 90 degrees, big change, center. Just for proof. You can't really see focus, but bam, there's the big change in the gyro X and Y. There it goes again. Big change there. Pitch back, big change there. Pitch it forward, big change there. You might see a small bit of lag. That's because this is the debugger system as well. But there you go. There's the working IMU.
So this is the code for the quadcopter flight controller. And instead of running off of the shelf Betaflight like every other drone that usually uses that firmware, this firmware is something we wrote from scratch in C for the TI MSP M0 G3507 microcontroller, and it's running at around 16 megahertz. Right now it's about 1,000 lines of code, and it tried to handle motor output, which we partially were able to achieve via arming the ESC. However, the motor couldn't actuate due to issues with the ESC itself. And right now it handles IMU sampling correctly, so we do have correct interfacing with the IMU and a self-test sequence as well for the ESC. And although we were unable to accomplish the PID control loop and the radio receiver, we want to aim for those next. So the hard part of flying a drone isn't really the math. It's getting the four motor signals out of the chip cleanly. These ESCs, the electronic speed controllers that drive the motors, expect a digital protocol called DSHOT 300. That's a 16-bit packet sent at 300 kilobits per second, 1,000 times a second with a CRC, a checksum at the end. If even one bit is off, the ESC throws the whole frame away. And there are four motors, so four of these streams running in parallel all the time. Here's how my code handles that. I use three of the chip's hardware timers. One of them generates the bit clock and publishes a zero event every 3.3 microseconds. Four DMA channels, direct memory access, which uses the MSP modules that we didn't discuss in class. And this just means hardware that moves data around without the CPU touching it. And these are all subscribed to that event. Every time the clock ticks, all four channels independently shovel the next bit of each motor's frame straight into the timer's compare register. No CPU involvement at all. The CPU just stages the throttle values once per millisecond. The timers and the DMA do the actual transmission. That means a complete four motor frame burns about 56 microseconds of bus bandwidth and zero CPU time. Now here's the interesting story. The EC would never decode a single frame. Welcome beep on the power up, and then we'd receive silence. I'd verified the pin mapping, the CRC math, the bit timing, the DMA writes. Everything looked perfect on paper, but nothing was coming out. It turns out there's a register on this chip called CCPD, Capture Compare Pin Direction. By default, every pin on every timer is configured as an input. That's the factory reset value. You can set up the compare logic perfectly. You can route the pin through the multiplexer to the timer. You can tell the timer to drive it high on every period boundary. None of it matters because the pad itself is electrically disconnected from the timer's output driver until you explicitly flip CCPD to output. It's one line of code. It's actually missing from TI's own example PWM driver as well. The fix was to just or the right bits into that register at init time. There was a second bug which was also more subtle. The DMA fires on a zero event from the timer, and the CPU's job is to enable the DMA and then flip the output pins from idle to timer driven, both lined up with that same zero event. The original order was enable DMA, clear the event flag, wait for the next event. The problem is there's a 5 cycle window between enable DMA and clear flag. The timer fires within that window. The DMA silently consumes the first bit, and the CPU then waits for what is really the second bit's event. The pin flip happens 1 bit late, the frame is corrupted, the CRC fails, every frame gets rejected. I rewrote it as a 2-stage synchronization. Wait once to land on a known position, then sorry. The pin flip happens 1 bit late, the frame is corrupted, the CRC fails, every event gets rejected. I rewrote it as a 2-stage synchronization. Wait once to land on a known position, then arm the DMA inside the guaranteed quiet window, then wait again. And the second event is guaranteed to be the one the DMA fires on. CPU and DMA are now physically locked to the same edge of the same pulse. So that's about 933 lines of original code. A DMA orchestrated motor driver, a SPI driver for the IMU, a staged self-test, and a couple of subtle bugs that are basically impossible to find without going down to the silicon documentation. Next up is porting the gyro PID loop, hooking in the RC receiver, and finally seeing if this thing actually flies.
All right, I hope you enjoyed our presentation on the drone.